Yeah. So my topic for this talk is application specific instruction set processor, also called ASIP. Its design methodology and design issues. This approach, which is comparatively a new approach to realize a processor or programmable processor for a targeted application domain, can deliver huge performance and power benefits while regaining the advantage of flexibility or through software programmability. So this is a new approach. So before going to this approach, we will discuss or we will see the alternate approaches that are available for the designer to implement a logic. Then I will briefly discuss about ASIP approach, ASIP design methodology that we have used to design this ASIP. Then we will see the design steps that we follow to design the ASIP, complete ASIP right from the scratch, and then we implemented this ASIP onto the FPGA. Okay, before going for the ASIC implementation. Then we compare this design ASIP with a general purpose kind of processor. Okay. We do the performance comparison, and finally I will conclude my talk. So the first approach that is available to a designer is an ASIC approach. This is very simplest approach. So in this approach, what we will do, we will simply map the algorithm directly onto the hardware. Okay. हम डायरेक्ट algorithm या functionality होती है, ठीक है? Then we'll implement this functionality directly onto the hardware. So this is the simplest approach. This approach will give highest performance. Okay, सबसे ज़्यादा performance यही approach देती है, जिसमें हम directly hardware में implement करते हैं. And also the power distribution would be less in this approach. So these are the advantages of this approach. But the disadvantage with this approach is that it will not provide any flexibility. Now what do you mean by flexibility? Flexibility means, if suppose your application or your functionality changes, okay, then you have to redesign your hardware, okay, or you have to redesign your ASIC. अगर आपका एप्लीकेशन या फंक्शनैलिटी आगे चेंज होता है, ठीक है, तो आपको हार्डवेयर दोबारा से डिजाइन करना पड़ेगा. उस हार्डवेयर को जो पहले डिजाइन किया था उसको फेंकना पड़ेगा, एंड यू हैव टू रीडिजाइन योर हार्डवेयर. सो दिस इज द डिसएडवांटेज विद दिस अप्रोच. These architectures, they can be combinational. So I am assuming that you have undergone the digital design course in your degree. सबने पढ़ा है digital design course? उसमें combinational, sequential सब पढ़ा है, right? RTL level design, how to do the RTL level design. I am assuming that you know how a processor works. Processor कैसे काम करता है? सबने C program लिखा है? लिखा है ना? So that C program will be executed by the processor. Okay? Your processor executes that C program in sequence. So that is why they are called sequential languages, because all these statements, they are executed by the processor in sequence. Okay? So there is a sequential processor available underlying the architecture or the BICON architecture, and it will execute all the statements that you write in your C code. This is how this processor works. So the second approach that is available to a designer is a general purpose processor based kind of approach. Okay. So you use processor in your laptop, you use processor in your PC. They are all general purpose processor. Now why they are called general purpose processor? Because they can implement any logic. Okay. You write program. So program is nothing but a sequence of instruction. आप कोई भी प्रोग्राम लिखो, वो प्रोग्राम आपका प्रोसेसर एग्जीक्यूट कर देगा. So that is why this is called general purpose processor. So it can implement any application or it can implement any logic. So it provides full support of programmability. So here you will get maximum degree of flexibility. Okay. But the disadvantage with this approach is that it is very slow. It will not give high performance, so the speed is very slow. Why? Because this processor doesn't have dedicated hardware functional blocks like ASICs in the execution unit. If, for example, if you want to execute a cosine, if you want to compute a cosine of a number, ठीक है, अगर C में आपको cosine function अगर compute करना है, तो आपको क्या करना पड़ता है? You have to include the math.h header file, right? या एक्सपोनेंशियल किसी नंबर का निकालना है, then again you have to include this header file. तो इसका क्या मतलब है कि there is no direct hardware support available for all these functions. So there is a subroutine defined in these header files. So you have to execute those subroutines to compute the exponential or sine cosine function. So generally this is slow. ठीक है, ये slow हो जाता है because for example you all know how a processor works. तो सबसे पहले आपका प्रोग्राम मेमोरी में रहता है, ठीक है. So you have to fetch the instruction from the program memory. So you require one memory operation. Then you have to decode that instruction, what that instruction does. Then you have to fetch the operands from the data memory. So this is another memory operation. Then you have to execute, and then this generated result will be again stored back into the data memory. So you require only 3 memory operations. And these memory operations, they are very slow in hardware. Okay. So they are the bottleneck. Okay. In determining the performance. So for example, if your sine or cosine or exponential function require 100 such instructions, okay, and one instruction will take 3 memory operations. So you require generally 300 memory operations, okay, to execute this instruction, to execute this operation. Right? So this general purpose processor based approach is slow in computing the logic, and also they consumes a lot of power because all these memory operations they will be done via buses. Okay? Memory से आप fetch करते हो, then the data will go to bus, and then again will store the data into the functional unit, or it will go into the execution unit. Okay, so the data transfer is via bus, and this bus they are nothing but they are group of wires. So there is a heavy capacitance associated with these wires, and we all know that power dissipation is directly proportional to the capacitance. जितना ज़्यादा capacitance होगा उतना ही power dissipation आपका बढ़ेगा. So as a designer, as a VLSI designer, I have to reduce this power dissipation. So I have to reduce this capacitance. ठीक है, तो जितने कम memory operations होंगे उतना ही कम आपका power dissipation होगा. Another approach that is available for a designer is the programmable digital signal processors. So this is a specialized, this is also a general purpose processor, but only suitable for a DSP kind of application like your IR filters, FIR filters. Okay. Again, this is slow. Another approach is hardware software co-design, where you implement some portion of your logic in the software and implement some portion that is frequently required by your application in hardware. So we do co-design kind of approach using this approach, like your hardware of your mobile. So there we use hardware software co-design. So there is a SoC, system on chip. Okay. So that is designed using hardware software co-design. Okay. So this is another approach that is available for the designers. Now by seeing all these approaches, we can conclude that to achieve ASIC-like performance, where we directly mapping to the hardware, algorithm is directly mapping to the hardware, one needs to build algorithm-specific high-performance hardware functional blocks. There are also mini ASICs in your design, and to provide programmability, because we require programmability also, so that there would be flexibility. Okay, and this flexibility comes from the definition of instruction set. So we have to define the instruction set for that processor. So one needs to define specialized instructions. Okay, not the instructions that are available in the general purpose processor. We have to define specialized specialized instructions. For example, we have to define a single instruction for exponential function. We have to define a single instruction for cosine computation. So these are not general instructions. They are specialized instructions. Okay. So this is the ASIP approach. Okay. So this ASIP approach generally bridges the gap between the ASIC and the general purpose processor based approaches. Now to realize this application, now the question is, what should be the application to demonstrate and test this ASIP approach? So we have chosen a parametric speech synthesis that will convert text into speech in real time. Okay, and its public, its C code is available in public domain, and it is developed by DH client. So it is available. So we have taken this C code, okay, we have taken this application, and we have designed the ASIP for this application. Okay. and we have demonstrated that we are getting the speech. The speech is generated in real time. As soon as you hit the text, as soon as you enter the text, the speech would be developed in real time. So this is the design. So I will not go into the details because the time is less. So these are the steps of the ASIP design methodology we have adopted to design this ASIP. So the first step in the design process is the application analysis. Okay. So you can do the application analysis using tools. So अगर आप Unix operating system use करते हो तो there GNU Prof is a tool available to do the profiling. ठीक है, तो GNU Prof टूल है, उस टूल से आपने जो C कोड या कोई आपका कोड है उसको आप उसको दोगे as an input, so it will give the number of functions that is required by that code. It will also give the operations that it uses. Okay, so all those information will be given by that tool. Okay, so you can use GNU Prof as an application tool, application analysis tool. So we have done the application analysis of this C code that is available with us. So I'm not going to the details of all these functions. So these are the functions that are required by this application, and you can see now this speech is processed frame by frame. Okay, just like your video processing. Video processing में भी यही करते हैं, images रहती हैं, and we'll process all those images one by one. तभी तो वीडियो दिखता है. आप 27 फ्रेम रेट्स पर सेकंड में आप करते हो प्रोसेस, तो आपको वीडियो दिखता है, अदरवाइज तो कोई इमेजेस नहीं है सीधा. So similarly, we will do the speech processing frame by frame. So this LP resonator, this is a second order resonator filter. So you can see in the table that it is the frequently required function. So it is required 960 times in one frame. Okay. Similarly, this natural source, it will compute the natural sourcing output. So it requires 240 number of times. Gen noise, this function computes the average of 12 random numbers. Okay. So again, this function is required 60 times in one frame. Now all these functions, they require operations, arithmetic operations and mathematical library functions. Okay. So here, this table gives the frequency of these operations required by these functions. So this get host, so it will take the parameter from the outside, from the host environment, and supply these parameters to the ASIP. So this get host function, it requires 4 addition subtraction operations, and all these operations are floating point addition subtraction operations. They are not fixed point. Okay. So it requires 4 addition subtraction operation, 20 multiply operations, and 3 division, floating point division operations. So in this, so you can see the table here. So all these operations require this much number of operations. Now all these operations that we added, all these operations, so this table shows that this addition subtraction will require 3417 times to process one frame. Okay. So now the real time constraint to process this one frame is 5 milliseconds. So this 5, we have to process this frame within 5 millisecond time. So it means we have to process 200 frames in 1 second. Okay. So then we have multiplied this addition subtraction operations, and this much number of operations we require per second. So now based on this application analysis, so this step will become the guidance for ASIP instruction. So now based on the application analysis, we will select the instructions. What would be the instruction in the instruction set of this ASIP. ठीक है, तो हमने application analysis कर लिया. ठीक है, अब application analysis करने के बाद हमको थोड़ा idea हो गया कौन-कौन से operations, कौन-कौन से functions हैं जो कि बहुत ज़्यादा बार कॉल हो रहे हैं. ठीक है, those are frequently required by the application. हर कौन सा function कितने operations ले रहा है, ठीक है, वो idea भी मिल गया. तो now I can decide the instruction set of this ASIP. ठीक है, so now I get an idea. See what would be the instructions in the instruction set of this ASIP. So this LP reson, so it is frequently required. So I have decided that I will give one instruction, one application specific instruction for this function. Gen noise, again this is frequently required by the application. So I give one instruction, specific application specific function for this instruction. Similarly, I require cosine and exponential applications. But this type of instruction, you will not get this type of instruction in a general purpose kind of processors. So these are application specific instructions. Right? Then convert IF, that will convert integer to floating point, and again floating point to integer. We require this type of instructions to execute this code. So we keep two instructions for this. We also require rounding kind of operations. So we keep one instruction, application specific instruction for round, and we keep one instruction for lookup, because we have to convert the decimal values into linear values. So we keep one instruction, that is lookup, look underscore app, for this as an instruction, as an application specific instruction. So now I have to decide the clock frequency, at what clock frequency my processor work. मेरे को decide करना पड़ेगा, जैसे for example your Pentium or your Intel processor was at 3 GHz. So what do you mean by that? तो इसी तरीके से I have to decide the clock frequency before designing this ASIC. So I have given some clock cycles based on our prior experience to all these functions, to all these operations, and then we counted that to process one parameter we require total 62,675 cycles, total number of cycles. Okay, and we all know that with execution time to compute one frame is 5 milliseconds. So the required clock frequency would be the total number of clock cycles divided by the execution time. So it's come out to be 12.535 megahertz. So now we also require some more cycles to fetch for other operations like input, output, data fetch, data store, instruction fetch cycles. So we have not counted all those cycles here at this stage. So we have decided that we will keep a clock frequency of 25 megahertz for this processor. Now we have the next step is the proposition of data path or the microarchitecture for this ASIC. This is the block diagram of this top level diagram of this ASIC, designed ASIC. This would be the microarchitecture of the complete ASIC. Here you can see all these blocks. They are not simpler blocks. They are dedicated hardware blocks. So all the algorithms and their associated controller, they are embedded on all these blocks. This first block, this MP4, this is a program memory. ISC, it is a block that will compute integer, add, subtract, and then also do the comparison on the two numbers, on two integer numbers. FSC is a floating point addition subtraction block. FMPY is a floating point multiplication. FDV is a floating point division functional block. S cos compute the sine cosine. S exponential do the computation of sine exponential of a number. IJ computes the average of the 12 random numbers. Okay. And all these blocks, they are mini ASICs. They are not simple blocks. Okay. And all these blocks, they are connected with a single bus. Okay. And also they are connected with a control bus, C bus. So this controller will supply all the controls to this block. So we have used it distributed kind of control here in this architecture. So all these so what operation all these blocks have to perform, this would be decided by the controller. So this controller will provide the control signals to all these blocks, and that will be via control bus. Right? And then PCLU for because my PC points to the address of the next instruction to be fetched. PC program counter. Okay, so this block will do the PC related operations like PC incrementing or decrementing. Instruction decoder, it will decode the instruction, and this output of this instruction decoder will be going as an input. It will decide what would be the address of my next micro instruction or control word. So all my controls, they are stored in a control memory. So generally there are three kinds of implementation available for a control. कंट्रोल को इम्प्लीमेंट करने के लिए तीन तरह के ऑप्शंस रहते हैं. एक होता है आपका हार्डवायर्ड, तुमने पढ़ा है सब मोरिस मैनों में, हार्डवायर्ड अप्रोच और आल्सो कॉल्ड रैंडम लॉजिक इम्प्लीमेंटेशन. देयर यू इम्प्लीमेंट द कंट्रोल यूजिंग गेट्स और लॉजिक गेट्स. द सेकंड अप्रोच that is available to implement the control is micro-coded approach, where you store all the controls in a memory or in a ROM, and then you fetch all the controls, associated necessary controls to supply the controls to the associated blocks in the microarchitecture. DMAO, this block will generate the data addresses for the data memory. So we have to store two type of data, integer. MINT will the memory required to store the integer data. MFP, this is a memory required to store floating point data. this input interface block, it will take the data from the host environment. This outC, it is a, so this input interface and outC, we have designed them as a handshaking protocol. Okay. Both these blocks they are itself they act as a controller and they work in a handshaking environment. And this outC controller, outC block will send the output data for the generated results to the D2A converter, because we have to produce the speech. So this digital data will be converted into the analog. So these generated results will go into the DA converter and they are sent by the outC block. So this is an internal diagram of the controller. Again, I think I'll skip. I'm already running short of time. So we have decided we will have total 44 instructions. We have decided that we will keep 44 instructions for our ASIP. Okay. And they are classified into 4 groups: arithmetic, data move, program control, and special application specific instruction. So arithmetic instruction total 16. We have got 16 instructions. For data move, ठीक है? डाटा को एक मेमोरी लोकेशन से आपने 8085 में प्रोग्रामिंग की है, सबने लैब किया ना, वहाँ पे आपने कॉपी इंस्ट्रक्शंस, मूव इंस्ट्रक्शन वो सब यूज किया ना. So to move data from one location to another, so these kind of operations will require. So for that, they are called data move instructions. For that we get 12 instructions. Program control instructions, आपने C कोड में लिखते हो जैसे if this condition then ये करो else ये करो. So ये जो operations होते हैं they are called control statements. So here we require jump branching kind of thing. You require branching instructions to execute this kind of operations. ऐसे statements होते हैं. So we also require branching kind of instructions. We also require loop statements. Okay? So loop statements are also there in our application. So we have kept 2 loop instructions, one to start the loop and one to end the loop. And then we also keep instructions for subroutine call. Okay? So one instruction is required to call the subroutine, and then after executing all the instructions that are there in the subroutine, we have to again return the control back to the program. So we require return statement, return instruction. And we have already seen these application specific. So we have kept 8 application specific instructions that you will not see in a general purpose kind of processors. These are the instruction format we have defined for all the 44 instructions. Example, so this instruction word is a 32-bit instruction. Okay? So this team FC, it will divide one floating point number to a floating point constant. What does this instruction do? It will divide a floating point number that is given by this address given in PTR1 field. Okay? So it will, this address will go to the floating point memory. So it will fetch the operands from the floating point memory, and this number is divided by this constant that is supplied within the instruction. So this instruction will come as an extension word with this instruction. Okay. This first. Okay. So we have total 44 instructions. So we require 6 bits to encode all those instructions. ठीक है ना? 32 के लिए 5 चाहिए bits encode करने के लिए. 32 से ज़्यादा चला गया तो we require 6 bits. 44 instruction है. So we require 6 bits to encode. We require 10 bit for data address. We are not using these 3 bits, and then this extension word. So this 32. So we are using IEEE 754 standard for floating point data. So I require 32 bits. So this constant is coming as an extension word to the instruction. So in this way we are encoding this opcode. So we have kept 00 for arithmetic, 01 for data move instruction, 10 for program control instruction, and 11 for application specific. So this is div. So this comes under the category of arithmetic. So we have assigned 00. Okay, here 11 means we have defined 4 categories for all the instruction. One is when we have to do the operation integer. Okay. When both the operands are integer, then we encode 00. Okay. When one is integer and other is constant, then we encode 01. And when one is floating point, when both the data are floating point, then it is 11. 0. And if one is floating point, another is floating point constant, then it is 1 1. So here this is 1 1. Okay, for category. And for member operand, again 1 1. So in this way we have encoded all the opcodes or defined all the instruction bit width. Instruction bit width is an example of branch. So now the next step is to implement the control part. Okay. So for control part implementation, we have used the hardware flowchart methodology. So this is a very powerful technique used at the RTL level, register transfer level. सबने पढ़ा है इसमें register transfer level. So at that level we have to capture the register transfers. आपके जनरली प्रोसेसर्स या कोई भी synchronous digital system हो, उसमें होता क्या है? We have to take data from one register. We have to do the combinational processing, and then again we have to store the result back into a register. So this is one register transfer. Okay? Register RTL level डिजाइन पे क्या होता है? Register transfers ही होते हैं. ठीक है? तो कोई भी सिस्टम हो, ठीक है? Any digital system, any synchronous digital systems, we have to capture these register transfers at the RTL level, register transfer level. ठीक है? So this hardware flowchart methodology, this is a very powerful tool used at the RTL level. But to capture the RTL level activities on a clock by clock basis, on a step by step basis. तो जैसे आपने FSM पढ़ा है, फाइनल स्टेट मशीन मिलीमीटर पढ़ा ना, तो there आप स्टेट मशीन यूज करते हो. So that state, we have to capture that state using hardware flowchart methodology. We will see by taking an example. So this is not going to be detailed. This is how a flowchart looks. Okay. So here you define your register transfers, operations or tasks. Here, then you define the access type, whether you are reading from the memory, you are doing the writing to the memory. So you can define data read, DR, DS, or IR, whether you are reading from the instruction or fetching the next instruction from the program memory. Operation type, whether you are performing addition operation or multiplication operation. So here in this field you can define this part here. So this will give the next state transition. The next, how you are accessing the next micro instruction from the control memory. So here, if you are accessing the micro instruction next, then it is called DB, direct branch. Okay. If you are fetching the next micro instruction, then this is DB. Okay. So you can define DB here. If your micro instruction, if your address of your micro instruction comes from the instruction itself, then it is called IB. So here you can specify whether it is DB or IB. This state ID will tell me my present state. Okay, this type, this state ID. Okay. So this will give me my present state, and this next state would tell what would be my next state. Okay. So after completing this state, where I will go. So this next state ID will give me the next state. So before writing the hardware flowchart methodology, you have to define the rules of operation. Okay, so I am not going to do the details. So we have defined the rules of operation. Okay, so these are the rules of operation we have defined. Now we'll see an example of an exponential instruction. So this is the opcode for the exponential instruction. This the operand address will be given by the source PTR2. Okay. And then the result will be stored at this destination PTR1 field. So this address will be given by this 10-bit field. Okay, where you have to store the result. So these are the hardware flowchart we have written for exponential function. First, this PTR1 field of IR will go to the PTR1 range. So first of all, you have to store the destination address in the PTR1 range. Okay, and this PTR2 field where you have to fetch the operands, this will go to the floating point memory because this data is available in the floating point memory. So it will go as an address to this floating point memory. Okay, to fetch the operands. Then this, so it will take one state. Okay, or one clock cycle. So at the RTL level, every designer has to ensure that all these register transfers will be done in one clock cycle or in one state. एक clock cycle, एक state या एक step सब कुछ एक ही चीज होती है. ठीक है? एक स्टेट में, ठीक है, हम क्या काम करते हैं, जितने भी ऑपरेशन करते हैं एक साइकिल में करते हैं. ठीक है, तो वही हमको कैप्चर करना है यहाँ पे, all the register transfers. ठीक है. Then the result of this floating point memory जो हमने डाटा एक्सेस किया है, that is available in this register. it will go to the F2IS block. ठीक है? तो जो हमारा block है exponential function का, it is not a floating point exponential block. So first of all, you have to convert this floating point data into special format, which is a 25-bit format. ठीक है? So we require one special block to convert this. So first it will go to the this data will go to this block via bus. ठीक है? So again it requires one state. So here, so this block F2IS it needs one clock cycle to compute its result. So this state is free. So in this state, what I am doing? I am doing the PC incrementing because this state is free. So I can do this operation task here. Then now the result of this F2IS block is available. Now this register R0 register F2IS, it will contain the output of this F2IS block. So it will be gone. So it will be going to the input register of the exponential block. और ये exponential block exponential compute करेगा. So we have to load this data to the input register of this exponential block. Now this exponential block will take 54 clock cycles to compute the result. इसको 54 cycles लगेंगे, ठीक है, compute करने के लिए. So the next state, so अब प्रोसेसर को वेट करना पड़ेगा 54 clock cycle के लिए, ठीक है. तो जब आपने लोड कर दिया, तो then this processor goes into the wait state. Now it is waiting for the result to come, ठीक है. So ये जो वेट काउंट है, it is 54. It will go into this wait counter. This wait counter is a down counter. तो हम 54 इसमें लोड कर देंगे and it will do the down counting. जब ये 0 हो जाएगा, it means my wait is over. So I go into the next state. Okay. If it is not 0, then I will remain in the wait state. Okay. And when this result is available, then this result is available in this R0 exponential output. It will again go to the S2 block. It will convert this special data back again to the floating point. Okay. Again it will take one clock cycle. So here I am fetching the next instruction. PC goes to program memory. My program counter goes to the program memory. That means I am fetching the next instruction from the program memory. And then this result from R0 register S2F is going to the floating point memory. So again I have to store this result in the floating point memory. And this address that I have stored in the first state PTR1 range goes as an address to the floating point memory. So at this address, the result will be stored. So this is an example of how we have designed the instructions. So we have written hardware flowchart for all the 44 instructions in this way. Okay. Now, after writing the hardware flowchart for all the 44 instructions, the next step is to design the control or to derive the controls from the hardware flowchart. ठीक है, जो माइक्रो इंस्ट्रक्शन जो प्रोग्राम जो कंट्रोल मेमोरी में जाएंगी, ठीक है, वो कैसे होंगी, ठीक है, तो उसको डिजाइन करने के लिए हम देखेंगे. So this will be the format of my control word field for the micro instruction. So we have used the horizontal microcoding approach to design the micro instructions. So all the fields they are defined. Okay. So this is a 60-bit control word. Okay. So we have defined the fields for all the operations. You can see the details here. The field 1 will be a program memory access controls, and we have encoded these 2 bits. So when the 00, no operation. When 01, it will read the instruction from program memory. So in this way, we have encoded all the control fields, all the 15, 17 control fields. And now we have to derive the control words from the hardware flowcharts. So we have to design the micro instructions. So here, so this is the first state of a add II instruction. So this PTR1 field of IR, it will go to the PTR1 range. Okay. So this is my first operation. So the first operation is PC increment. So I have defined 001 for PC instruction. PC increment for integer memory. I'll encode this control as 01. Okay. For data rate, I'll encode as 00. Okay. So according, by seeing all the operations, or by seeing all the register transfers, I am deriving the controls from the hardware flowchart. So we have derived the controls for all the states. Okay. So these are the 5 micro instructions required by this add II instruction. Okay. So in this way we have derived the controls. Okay, finally I'll conclude. These are the functional blocks, architecture of the functional block that we have designed. I'll not go to the detail. These are the synthesis results. So we have implemented all these blocks on the FPGA. So these are the results, synthesized results. Then we have done the testing. I'll not go into the philosophy of how we have done the testing of these functional blocks. Then how this is the input interface protocol that we have designed. This would be the timing diagram. So this is a handshaking protocol. This is the controller that we have designed for output controller block. So this is the approach that we have used for integration of the full ASIP. This is the overall synthesis results of the complete ASIP on the FPGAs. Now this is the performance comparison. Now we have to prove that the approach or the methodology that we have adopted is better than the other approaches. So we have compared our ASIP with a general purpose kind of processor. So we have taken Leon 3 processor. So we can see here that this cycle count to compute this ASIP is only 82,000. And this Leon 3 is taking 7 lakh clock cycles to compute this, to realize this application. And power, so it is, the power dissipation is only 28 milliwatts in case of ASIP. But here, it will dissipate 1 watt of power if you are executing this application onto a Leon 3 processor. So we have seen that this approach, the methodology or the approach that we have taken is giving me the higher performance, and also my power distribution is as low as possible as compared to other general purpose processors. Conclusion. Thanks. So here you can't pipeline this architecture. This is not a pipeline architecture. There you use as pipeline architectures, because here most of क्वेश्चन क्या है कि ASIP approach हो, ASIC approach का upgraded approach है, ये करें. This is the question.
Basic difference between ASIC approach and ASIP approach.
ASIP and ASIC. ASIP मैंने बताया ना स्टार्टिंग में कि ASIP के अंदर we are providing instructions to provide the support for programmability. In ASIP, you do not have support of instructions, so you can't, you do not program ASIC. So there is no flexibility in ASIC. So ASIC is आपका एल्गोरिथम उसको डायरेक्ट आपने हार्डवेयर पे इम्प्लीमेंट किया, आपने कोई इंस्ट्रक्शन प्रोवाइड नहीं की एग्जीक्यूशन यूनिट, तो वहाँ पे हम वो अप्रोच यूज कर रहे हैं डेडिकेटेड वाली. बट वी आर आल्सो प्रोवाइडिंग इंस्ट्रक्शन सपोर्ट टू सपोर्ट प्रोग्रामेबिलिटी, कि अगर बाद में आपका एप्लीकेशन चेंज भी होता है तो आपको सिर्फ प्रोग्राम में चेंज करना है, हार्डवेयर में चेंज नहीं करना है. सो योर इंस्ट्रक्शन विल बी डीकपल्ड टू द हार्डवेयर. इंस्ट्रक्शन आपका यहाँ पे है, हार्डवेयर यहाँ पे है. तो अगर आपका एप्लीकेशन में कुछ चेंज भी होता है तो आपने ये इंस्ट्रक्शंस यूज किया है अपने एप्लीकेशन को रियलाइज करने के लिए, तो आपको प्रोग्राम में चेंज करना है, हार्डवेयर में चेंज नहीं करना. तो ये वाली ASIC के अंदर ये फ्लेक्सिबिलिटी नहीं होती. ASIC में अगर आपका एप्लीकेशन चेंज होता है तो आपको अगेन यू हैव टू रीडिजाइन द हार्डवेयर, दोबारा से हार्डवेयर डिजाइन करना पड़ता है. सो देयर इज नो फ्लेक्सिबिलिटी. बट इन ASIC यू हैव द फ्लेक्सिबिलिटी, क्योंकि हमने इंस्ट्रक्शंस प्रोवाइड कर दिया है, हमने हार्डवेयर को डीकपल कर दिया है, ठीक है, विद इंस्ट्रक्शन सेट. तो अब आप इंस्ट्रक्शन सेट को यूज करके अपना एप्लीकेशन रियलाइज कर रहे हो, जैसे आप C में करते हैं. आप C में प्रोग्राम लिखते हो, ठीक है, तो अगर आपका एप्लीकेशन चेंज भी होता है तो आप C में चेंजेस करते हो. तो मॉडिफाई योर प्रोग्राम को मॉडिफाई कर लो. आप हार्डवेयर तो चेंज करते नहीं हो, क्योंकि सेम CPU रहता है, सेम PC रहता है, उसको चेंज थोड़ी करते हो, हार्डवेयर चेंज थोड़ी होता है. तो सिमिलरली हियर आल्सो योर एप्लीकेशन यू हैव टू डू द चेंजेस इन योर एप्लीकेशन और इन द प्रोग्राम. योर हार्डवेयर रिमेन्स द सेम.
Now, I would like to request for this session as a chairperson.
Process I'm designing a E-shaped patch antenna with using different substrate material. I'm using a HFSS software for this simulation purpose. These are the outlines. Before going on, I'm telling about you basic antennas. What is an antenna? What is an antenna? Antenna is a transducer which converts one energy form to another energy form. And which energy form it uses? electric energy into electromagnetic energy, and it receives electromagnetic energy at the receiver end. Okay. These are the outlines, overview of microstrip antenna, feeding methods of microstrip antenna, characteristics of basic patch microstrip antennas, my design and the simulation result, conclusion and references. I am using this microstrip patch antenna for microwave frequencies, and microwave frequencies are greater than 1 gigahertz. It is usually consists of a metal patch on a dielectric substrate, and the other side it has a ground plane. The patch may be in a variety of shapes, but rectangular and circular are most common. The variety of shapes are, we can use rectangular, square shape, circular, annular ring, triangular and elliptical shape as a patch on the microstrip patch antenna. Advantages of microstrip antenna. These are the low profile antenna, easy to fabricate, easy to feed, easy to use in an array. Patterns are somewhat hemispherical with our moderate directivity. Disadvantages of microstrip antenna. Low band, it has low bandwidth, efficiency may be lower than with other antennas. If we compare Yagi-Uda antenna with microstrip antenna, then this antenna has lower efficiency. Efficiency is limited by conductor and dielectric losses, and we can consider the surface wave losses also. We cannot handle extremely large amount of power due to dielectric breakdown. Applications of microstrip antenna. We can use microstrip antenna as a satellite communication, microwave communication, cell phone communication and GPS antenna. Feeding methods. We are using feeding for connecting our source to antenna. We have 4 different feeding methods for a microstrip patch antenna. One is coaxial feed. In this we connect a coaxial cable with the patch, and in this process the lower layer shows the ground plane, H shows the thickness of the dielectric material, epsilon r the permittivity of dielectric material, and the upper layer shows the patch, and the coaxial cable are connected at the midpoint of the patch. Advantages of coaxial feed. It is simple, directivity is compatible with directly compatible with coaxial cables, easy to obtain input matches by adjusting feed position. We can change the feed position and easy to obtain input match. Disadvantages. Significant probe feed radiation for thicker substrate. If we use a thick layer of substrate, then the radiation by the probe occurs. So this is the main disadvantage of coaxial feed. It is not easily compatible with arrays. If we design arrays, then it is not compatible because we are not connecting more than one coaxial cable with the patches. So we for this purpose we use microstrip patches, microstrip lines for connecting patches with input signals. The other is inside feed. We can also call microstrip feed, and it has advantages of, it is also simple, Also for planar feeding, it is used for planar feeding. Easy to use with arrays, easy to obtain input matches. And it has a disadvantage. If we use a thicker substrate, then the radiation occurs. For deep matches, patch current and the radiation pattern may shows distortion. The third one is proximity coupled feed. It has in this process a ground plane, then a dielectric substrate, then a microstrip line, and then also a dielectric substrate, and then mount a patch on the dielectric substrate. It has advantage allow the planar feeding, less line radiation compared to the microstrip feed, higher bandwidth it is allowed. Disadvantage requires multi-layer fabrications. Alignment is important for input match. Fourth one is gap coupled feed. In this we have a gap between the patch and the microstrip line. It has an advantage. It is also used for the planar feeding, and it can allow for a match even with a higher edge impedance. If we use a high impedance surface, then we use this gap coupled feed. It has also disadvantage requires accurate gap fabrication. We required a accurate gap between the patch and the microstrip line and requires full wave design. Aperture coupled feed. In this process, the lower layer is ground and then dielectric and then a layer of metal, and we have a slot on this layer and then mount a patch, then another layer of dielectric, and then a patch is mounted on that dielectric. It has advantage, allows for planar feeding, feed line radiation is isolated from patch radiation, allows for use of different substrate to optimize antennas, feed, circuit performance. Disadvantages requires multi-layer fabrication. Alignment is important for input match. Now the other part is characteristic. These are the characteristic of normal patch microstrip antenna. In this, the bandwidth is directly proportional to the substrate thickness. The probe inductance become large enough so that matching is difficult. The bandwidth will decreases. The bandwidth and gain is inversely proportional to the dielectric constant. The bandwidth of rectangular patch is proportional to the patch width. Proposed design, which I am designing. I am designing this type of patch antenna, and I am using a coaxial feed in this design. And after that, I am changing two dielectric substrate. One is FR4 epoxy and second is epoxy Kevlar. FR4 epoxy have permittivity 4.4 and epoxy Kevlar has 3.6. And now I am measuring the gain and radiation pattern and the return losses of due to these material changes. If I am using FR4 substrate, then operating frequency we can also call resonant frequency at this time, and 9.8 gigahertz, and get the return loss minus 21.4158 dB, and the gain is obtained at this frequency is 4.45. This one is shown in next slide, and then I am using the zero angle radiation pattern, and then I have got the magnitude of 4.4564. If I am using epoxy Kevlar, then the resonant frequency or the operating frequency is 10.8 gigahertz and return loss is minus 21.2481 dB and the gain is obtained 6.2916. So we can see that the dielectric constant is reduced but the gain is increasing here. This is the conclusion. If we are using FR4 Kevlar or epoxy Kevlar, then FR4 Kevlar has the dielectric constant 4.4 dB and the epoxy Kevlar has a 3.6. Then the gain is increases when the dielectric constant is reduces. These are the references.